All right, this first bit is only going to those of you out watching this in video. I'm having the worst allergy day. I was cleaning over the weekend and now my face is swollen. My hands are swollen. I have eczema hiding under the suit jacket. I am miserable, but the science must go on. So if you see me wiping a tear from my eyes, which hopefully I won't do because I'm wearing glasses and that would go very poorly, it's not because I'm sad or upset. It's because dust is evil and is the enemy. And the science must go on. Anyways, hello and welcome to February. In this year, 2024, this always short month is just a tad bit longer as we add an extra leap day. That extra day is because it takes the Earth 365 days, 6 hours, and 9 minutes to orbit the sun relative to the stars. By adding an extra day every 4 years, we can take care of that extra 6 hours per year. Those 9 minutes are a bit more difficult, but they get handled by not having a leap year in new centuries that aren't divisible by 400. It is a bit complex, but it works. And now you know. You need to be prepared for a bit of calendar chaos as we move toward March. This particular February is one that also hopes to bring us the first successful launch all the way to orbit of a Starship rocket. And SpaceX gets one extra day to meet that deadline. In general, February is a good month for science. Historically, we've seen supernova 1987 go off, the births of Copernicus and Galileo, and even the discovery of Pluto. It even brought us an asteroid air blast back in 2013 when a 20-meter space rock exploded over Chelyabinsk, Russia in the early morning hours of February 15th. It's a small month, but it's a mighty month. And in today's episode, we bring you some mighty and new science. We have galaxy formation, supernovae, otters healing estuaries in an earth science kind of way, and even space toilets. All this and more is coming to you right here, right now on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and we are here to put science in your brain. The universe that today's telescopes observe is not the universe that was described in the textbooks of my youth, when all we had was the knowledge a Big Bang once happened and a local universe to observe. Theorists were able to build beautiful theories of slow and gradual formation and growth of structures as gravity pulled together first gas and later galaxies as large-scale structure gradually formed. But with each new larger and better telescope, we've found things that made our simple understanding not just lacking in details, but also just not quite right. For instance, because it takes time for structures to form, our generally accepted theories didn't anticipate the extremely bright galaxies that JWST is now finding. Theorists working to reassess how the early universe should actually look haven't yet explained the large bright systems we see. But a new paper appearing in the Astrophysical Journal Letters, with first author Claire E. Williams, postulates the existence of small, bright systems JWST should be able to find. In new and more complex models, the team looked at how luminous matter and cold dark matter interact. In the largest systems, things work as expected. Massive blobs of slow-moving dark matter draw in and hold on to fast-moving hydrogen and helium and compress the gas down into stars. In smaller systems, we have more of a damped oscillator. The regular matter streams at supersonic speeds, and in small systems they realized that fast-moving hydrogen and helium can blow right past the blobs of dark matter on its first pass and then fall back in millennia later. During this later infall, stars form all at once in massive star formation bursts that create small, exceptionally bright galaxies. According to Williams, quote, "The discovery of patches of small bright galaxies in the early universe would confirm that we're on the right track for the cold dark matter model because only the velocity between two kinds of matter can produce the type of galaxy we're looking for. If dark matter does not behave like standard cold dark matter and the streaming effect isn't present, then these bright dwarf galaxies won't be found, and we need to go back to the drawing board." End quote. The nice thing about this theory is that it is very clear that if you see this, then this thing is true. But if you don't see this, here's a bigger thing you need to worry about that isn't true. One of the ongoing debates in modern astronomy is the temperature or velocity of particles in dark matter. There are a lot of different reasons to think cold dark matter just might not work, but it's unclear. If this theory correctly predicts something no one knew to expect, then it's pretty good evidence that cold dark matter does exist, and our models just need more detail. Details like those in this paper. Gas dynamics are more than a little complicated no matter where you look. The dynamics of gas in and around forming galaxies, it's just particularly complex. Ideally, gas goes in and stays put. But now we know gas may sometimes go in and shoot right out the other side. And we also now know that sometimes gas goes in and the galaxy itself flings that gas back out. Observers looking at the quasar J2054-0005 have found clear evidence that the system is flinging molecular gas, the stuff needed to form stars, right out of the system. While you likely aren't noticing it right now, light actually exerts a pressure. The more light hits you, your car, or the outer layers of a star or galaxy, the more push that light can exert. Our own sun is a mostly spherical object because the inward pull of gravity is balanced against the outward push of light. The sun then gets a bit flattened because it's rotating. In galaxies, with an actively feeding central black hole, material will form what's called an accretion disk around the black hole, and that disk can get extremely hot and dense and generate a magnificent amount of light. This light makes quasars the quasi-stellar objects we know and love. That disk appears like a bright star, and it can be so bright we don't even see the surrounding galaxy. And that light from that disk can exert a powerful force that pushes gas away, sending it streaming out of the system. Or so the theory has gone. We hadn't exactly seen this happening, at least not until now. Observers led by Dragon Salak using the Atacama Large Millimeter and Submillimeter Array to observe the extremely bright quasar J2054-0005. Well, this particular telescope system lets them see the absorption lines of different gases in the bright rainbow of the galaxy's overall continuum of light. In this case, they saw OH, the molecule hydroxide, flowing out of the system. This gas outside of the galaxy is gas it can't turn into stars inside the galaxy. And thus, a theory has been shown to be true. The tremendous light of quasars' accretion disks can expel gas and suppress star formation. The more we look out at the universe, the more we're going to prove and disprove theories and find things that just plain were never expected. Case in point, while observing a cluster of galaxies as part of a JWST survey, researchers spotted a relatively nearby dwarf spheroidal galaxy peering back at them. This low-mass system is only about 98 million light-years away. It is so near and so diffuse that we can make out individual stars throughout the system. This work is published in the Astrophysical Journal Letters and led by Tim Carlton. We had thought dwarf galaxies consistently existed in the outskirts of more massive galaxies and orbiting within galaxy clusters. We had not thought they'd sometimes be hanging out apparently alone. And now we know. Sometimes galaxies just sneak off to be by themselves. How that happens? That's a future research paper. After the break, we're going to take a deep dive into supernovae and what they are showing us about the universe's expansion. Stay tuned. As a scientist, I get a lot of weird hate mail. There are the folks telling me relativity is wrong. There are the folks telling me NASA is keeping secret something like the Earth is flat, or the Senate has been taken over by aliens. And then there are the folks telling me that I need to open my eyes and look at the data, because scientists are otherwise too close-minded to notice what our data is telling us. Every time I get the digital, "Why can't you scientists just look at the data" lecture, it makes me wonder what people think scientists do. Because, really, all we do is look at data. And when that data tells us our understanding of the universe is wrong, we're pretty good, usually, not always, we're pretty good at accepting the data and throwing out false understandings, even when the data makes our life a whole lot harder. Back in 1998, this was what happened. Two different supernova research teams both found in their data evidence that our universe is expanding at an accelerating rate. Prior theory had indicated that the universe would forever expand at something close to a constant rate, or maybe slow to essentially a stop, or even maybe reverse course and collapse in on itself. The idea that it could expand at an accelerating rate was just a footnote. Sure, the math allows this, but this isn't math you need to explore because it just ain't so. It was something so ridiculous as to just be ignorable, which I was fine with. The maths of an accelerating, expanding universe are not something I wanted to ever solve. And had we thought that option was possible, someone would have made solving it a homework problem. I have solved this problem, just not as a homework problem. Anyways, with those two data sets published in 1998, we had to redo everything. Just 13 years later, an eye blink in the career of a researcher, the phenomena of an accelerating, expanding universe was generally accepted, blamed on a mysterious something we called dark energy. And the Nobel Prizes were handed out. Scientists are really damn good at looking at our data and recognizing when we need a new theory. And we still need a new theory. And maybe a new name, because dark energy is a really bad name. Anyways, since that cosmology disrupting discovery, the field of astronomy has made understanding the nature of dark energy a priority. And this has included looking for new ways to measure cosmic expansion, verifying the assumptions made in past data sets, and then otherwise trying to figure out what new data we need to acquire. One of the major projects in this search for dark energy has been the Dark Energy Survey. Using what were the most advanced cameras of their time, an international collaboration surveyed 5,000 square degrees of the southern sky to look for supernovae and to map out the large-scale structure of the universe. After the Big Bang, our universe was an almost smooth distribution of energy. Over time, that distribution got lumpier and a lot of the energy solidified out into matter, which then got lumpier and lumpier as it formed into clouds, then stars and galaxies, and then clusters of galaxies that formed even larger walls and superclusters of galaxy clusters. As we look at volumes of space that are further and further away, we get to essentially look back in time and watch this process in reverse. The further away we look, the longer it takes the light to reach us. And we get to experience the past in our far-off glances. We see the sun as it was 8 minutes ago. Pluto's light is from hours ago. The stars are years and centuries of light travel time away. Telescopes are time machines that only ever look backward. And with their amazing 570 megapixel camera, the 400 scientists from 25 institutions that make up the Dark Energy Survey collaboration, well, they have been able to look back in time and see large-scale structure growing. So far, this part of the survey hasn't radically changed our understanding, but it provides us a baseline understanding of what our theories must explain if they are valid. And this is one heck of a super important start. Along with their mapping, the Dark Energy Survey also looked at key areas of the sky once a week to explore for supernovae, to see if they could further refine the work done by those 2 Nobel Prize-winning teams in 1998. And in a new paper in the Astrophysical Journal, the Dark Energy Survey collaboration has published their final catalog of supernovae results. This release contains 1,500 new high redshift Type 1a supernovae, the kind formed when white dwarf stars are fed too much and explode. By measuring both the apparent distance to each explosion based on how bright they appear and the recession velocity of each point of light, we can plot expansion rates as a function of distance. There's a lot of error in those measurements. The supernovae have orbital velocities within their galaxies, and their galaxies have velocities within their clusters. Some systems are just a bit brighter or fainter naturally. Some are just weird stars that defy proper behavior. Stars are messy. But within the statistical noise of all these explosions is one simple truth. The data is completely consistent with prior observations. Our universe appears to be expanding at a rate that increases inexplicably over time. The weirdest thing about this is the dark energy seems to be constant with volume, such that as the universe expands, the dark energy stays the same density everywhere all the time without getting diluted. This is like imagining an expanding room with no way in or out that stays knee-deep with water no matter how big the room gets. Sure, if there was a vent for water to get added to the room constantly, this might make sense. But in a closed room, how does the depth of water stay constant as the room expands? How does the density of dark energy stay constant as the universe expands? We don't understand dark energy at the level of not knowing if it is just some intrinsic thing that space just has. If it is a force, a pressure, a leak of energy from the other dimensions we don't generally experience. We just don't know. But the Dark Energy Survey has shown us It really is there. And data set after data set are showing us pretty much the same thing. Hopefully, either time or additional data sets will help theorists find that bit of inspiration they need to figure out what factor is driving our universe apart. The supernova used to study the expansion of our universe, type 1A supernovae, are a case of small objects exploding when overfed. These explosions don't leave anything particularly chunky behind. Sure, there will be a supernova remnant and likely bits and bobs of former solar system. But when that white dwarf goes boom, the white dwarf goes away. But this is just one kind of supernova. Most kinds of supernovae are formed when a massive star runs out of fuel to use to produce light in their cores. During nuclear fusion, lighter elements are smooshed together into progressively more massive atoms. For things like hydrogen, carbon, and other small atoms, this process releases energy. Essentially, it takes less energy to have one helium-3 atom than it does to have 3 different hydrogen atoms. And that difference in energy is released as light. The light then creates a pressure that supports the star against gravity trying to collapse the star. For the most massive stars, fusion can keep going until iron. It turns out atoms heavier than iron require energy to be added to fuse them together. So at iron, fusion stops being useful. And a core that doesn't have fusion going on is going to stop generating light, stop supporting the outer layers of the star against gravity, and it's going to collapse, which is a process that admittedly adds energy into the system, so much energy that everything explodes as a supernova. According to theory, some of these stars will form neutron stars, some will form black holes, and some will simply blast themselves apart entirely. Since we see supernovae remnants containing neutron stars, we've put a lot of faith in these theories, but we hadn't been able to see a system go from star to supernova remnant with a neutron star in the center, at least not until now. In a pair of new papers published in Nature and Astrophysical Journal Letters, researchers led by Thomas Moore and Ping Sheng show that supernova 2022 JLI appears to have left behind a compact object that is consistent with the presence of a neutron star, or maybe a stellar mass black hole. A hungry neutron star, or stellar mass black hole, that is making itself known by taking chunks out of its companion. As the story goes, one star in a 2-star binary system exploded in May 2022. This particular system was in the nearby galaxy NGC 157, which makes it easy to observe. During the supernova, the smaller, less explodey star took a blow that caused its outer atmosphere to puff out. The compact object left behind when the larger star exploded then began to orbit through this puffed-out atmosphere, stealing material with its gravity and pulling a hot disk of material about itself. While the compact object is so far hidden, only a neutron star or possibly a small black hole can explain everything they are currently seeing. Short of having a supernova go off in our galaxy close enough to resolve a left-behind neutron star, and really, we may not want that to happen. Really, this is as close as we can expect to get to seeing a neutron star form. Sometimes the universe and the theorists are in perfect alignment. After a break, we'll be back to look at this week's Tales from the Launchpad. Stay tuned. This week, Erik Mattis is off dealing actually with technical difficulties with his internet provider. He'll be back as soon as his internet is back, and we hope that is soon. Anyways, this week's Tales from the Launchpad are still coming to you. They're just coming to you from me. Erik, get your internet back, please. There's about to be a whole lot of mispronunciations. Since our last show, we've had a couple of surprise Iranian launches, plus an evolution of the Virgin Galactic space tourism process, and a launch by Rocket Lab. Oh, and the usual Starlinks, of course. On January 26th, Virgin Galactic launched their 6th commercial spaceflight mission, Galactic 06. For the first time, they carried 4 paying passengers instead of the usual 3 passengers with an astronaut assistant. This change will allow them to clear their years-long backlog in less time. The 4 passengers were from Ukraine, Austria, and the US. Part of the Virgin Galactic's goal of normalizing spaceflight is to not disclose much biographical information about the passengers, unless the passenger is a scientist or important explorer of land, sea, and now space. The spaceplane reached a maximum speed of Mach 2.98 and an apogee of 88.8 kilometers before safely landing 56 minutes after its carrier plane took off. Next up, Iran, or more specifically, the Islamic Revolutionary Guards Corps, a military organization, launched a rocket called KM-100 on January 20th. The satellite, Suraya, will be used for communications, probably military, given the organization and the fact its launch pad is on a military base. Just over a week later, on January 28th, the civilian Iranian Space Agency launched a Simorgh rocket carrying 3 satellites into orbit from the Imam Khomeini spaceport. Unlike the KM-100, it used 2 liquid fuel stages and a solid 3rd stage. This was the first successful launch of the Simorgh rocket after 2 previous failures. The largest of the 3 satellites was made by the Iran Space Research Center, and it carries space component qualification payloads and other instruments to measure the forces produced by the launch vehicle, which will then be used to help design future payloads around this new rocket. The other 2 satellites were designed by an Iranian company and have Internet of Things payloads. Pre-launch photos were posted on the internet, but there haven't been any videos of either launch. On January 30th, a Falcon 9 launched the Cygnus NG-20 spacecraft toward the International Space Station. Let's watch the launch.
5, 4, 3, 2, 1, ignition, engines full power, and liftoff. Go Cygnus, go Falcon.
Falcon 9 and Cygnus begin their flight, taking aim on the International Space Station. Pitch and roll program are in. Falcon 9 parking out to the northeast.
Prior to this launch, Northrop Grumman was faced with a dilemma. They had 2 Antares rockets remaining after the Ukrainian factory that produced the first stage tank was blown up by the Russian military in February 2022. And no more engines as well, as the Russians refused to sell them anymore in response to sanctions imposed on Russia in response to their unprovoked invasion of Ukraine. Northrop Grumman were still contractually obligated to provide up and down mass to the ISS. And basically every other U.S. rocket was booked out until sometime in the 2030s, launching mega constellations or super secret squirrel spy satellites. That leaves them with only one option, the Falcon 9, and NASA finds itself in the uncomfortable situation of having the only active domestic cruise spacecraft and cargo resupply spacecraft both reliant on a single rocket type, namely the Falcon 9. Falcon 9 so far has an exceptional launch record, knock on wood. But this is space, and anything can and probably will eventually happen. Falcon 9 will launch at least 3 Cygnus, alternating with Cargo Dragon 2, until Firefly Aerospace can provide the replacement first stage for Antares. It will use the new Miranda engines being made for Firefly's medium launch vehicle. The Falcon 9's first stage returned to Landing Zone 1 at Cape Canaveral. The midday launch made for exceptional viewing, and the NASA launch meant that their fancy tracking cameras followed the stage down from space to the Earth on the live stream. Finally, on January 31st, Rocket Lab launched their four-of-a-kind mission from the second launch pad at their primary launch facility on the Mahai Peninsula in New Zealand. On board were 4 Skylark satellites for North Star Space, a Canadian company. Let's watch the launch.
5, 4, 3, 2, 1. And we have liftoff.
The satellites are for space situational awareness, detecting and tracking satellites in orbit and their signals. This sort of information is useful for determining the orbits of satellites and pieces of space debris very precisely for collision avoidance and proximity alerts if a satellite is getting too close to another satellite. Rocket Lab is under contract to launch 8 more satellites in 2 launches to complete the company's initial constellation. The Skylark satellites were originally going to launch on Virgin Orbit before that company went bankrupt about a year ago. Rocket Lab recovered the rocket's first stage from an ocean splashdown, like they've demonstrated in previous missions. The webcast was able to keep video stable on the returning booster throughout most of its return. They used a new grabber arm off the end of the recovery vessel to fish it out of the water, which they have only used once before. Rocket Lab stated no reused components were on the rocket. We track launches with the help of RocketLaunch.live. So far this year, the United States has had 11 launches, China has had 8 launches, Iran has had 2 launches, and India, Japan, and New Zealand have each had 1 launch. This makes the total number of launches so far this year 24. Finally, there are 10 toilets in space. Before we go, I'd like to share 2 things I learned this week that I never expected to learn. 1. Sea otters can weigh up to 100 pounds, which is way bigger than I ever expected. 2. Because sea otters eat 20 to 25% of their body weight in crabs and other critters every day, they have a massive impact on their environment. And it's actually a good one. For California coastlines where sea otters are returning after being hunted out of the ecosystem, researchers are now seeing creek beds and shorelines becoming more stable. As explained by Brent Hughes, quote, "Crabs eat salt marsh roots, dig into salt marsh soil, and over time can cause a salt marsh to erode and collapse. After a few decades, in areas the sea otters had recolonized, salt marshes and creek banks were becoming more stable again, despite rising sea levels, increased water flow from inland sources, and greater pollution. The return of the sea otters didn't reverse the losses, but it did slow them to a point that these systems could restabilize despite all the other pressures they are subject to. That suggests this could be a very effective and affordable new tool for our conservation toolkit." End quote. Put another way, if your coastline is overrun with crabs and your creek beds are falling apart in the face of rising sea levels and rough weather, try adding otters. And that's it for now. Good night, everyone, and remember to go out and look up.